This is your presenter Asloob Mudassar, and I am presenting slide number 96 of the course on laser physics. Question is, describe the most common incoherent pumping systems. What physical processes are involved in the generation of light from such lamps, and how the light is absorbed in the active media of important laser systems? The answer is a single flash lamp based pumping system is shown in figure 1. So this is figure 1 and the caption of the figure is elliptical cylinder containing active medium rod along one focal axis and the flash lamp along the second focal axis. So you can see that this is an encapsulating cylinder. The cross section of this cylinder is elliptical. So this is elliptical in shape. And this cylinder has being elliptical, has two foci. One is F1, the other is F2. Flash lamp is placed at one of the foci along this cylindrical shape, at one of the foci, whereas the active medium rod is placed parallel to the flash lamp along at the position of the second focus of the ellipse along its cylindrical path. So you can see that the flash lamp and the active medium rod are parallel to each other, respectively located at foci F1 and F2. And this whole assembly has a cross-sectional view as of a cylinder. So that's why this is an encapsulating cylinder. The active medium is in the form of a cylindrical rod lying along the focal axis of the cylinder. The flash lamp, identical in length and diameter to that of the active medium, is centered along the second focal axis of the cylinder. The cross-section of the encapsulating cylinder is elliptical, and the inner surface of the cylinder is specularly reflecting. That is, the inner surface of the cylinder is so smooth that it will follow specularly reflecting. That is, at each point of the inner surface, angle of reflection will be equal to the angle of incidence. The energy emitted by the lamp is focused on the active medium rod after a single reflection from the inner surface of the encapsulating cylinder. If it is required to focus the IR spectrum of a lamp on the rod, the inner surface of the encapsulating cylinder is vacuum deposited with silver or gold layers. So you see that if you are talking about, that is, if your active medium requires flash lamp light in the infrared region, then you can have an internal coating, that is the coating inside the walls of this encapsulating cylinder, and that could be of copper or gold. That could be of silver or gold, so that it can reflect efficiently the IR spectrum that is incident on the inner surface, so that the IR from the flash lamp is directly received by the active medium and also received through the reflection from the inner surface of the cylinder. But you see that if you are working in the other region, for example, in the visible region, you don't need silver or gold layers to be coated within the encapsulating cylinder. If the encapsulating cylinder does not have preference for elliptical cross-section, then the lamp and the active medium rod are placed as closely as possible, and the inner surface of the encapsulating cylinder needs not be specularly reflecting. For uniform illumination of the active medium rod, it is preferred to have inner cylindrical surface to be diffusely reflecting. This is shown in figure number 2. You can consider this figure. You see, this is the same this is a geometry similar to the previous one, where you have the flash lamp and the active rods are parallel to each other, lying parallel to each other. But you know that this is contained in a cylinder which is need not be cylindrical. So the flash lamp and the active medium are placed very close to each other, and they need not to be placed on the foci of the cylinder, because here we are not putting any constraint on the encapsulating cylinder. So this geometry could be placed in any container. For example, you can look at the shape of this container. It is not of cylindrical type. That is, the cross section is not cylindrical. So you can say that this is a non-encapsulating cylinder. So you can make a more correction over here, that you can write it as a non-capsulating cylinder. So it contains flash lamp and the active rods. Since this is a non-cylindrical geometry, so it is required that the flash lamp and the active medium should be very close to each other. And moreover, the inner surface of this geometry should be diffusely reflecting, so that it can uniformly illuminate the active medium rod when it receives light from the flash lamp. So this is the difference between them. So you see that here in the figure number 2, the caption, we have non-elliptical cylindrical cylinder containing active medium rod and the flash lamp in a closed assembly. So you can see that this is non-elliptical, though it could be of cylindrical shape, but this is a non-elliptical cylinder. You know that the advantage of the elliptical cylinder is that the light emitted from the one focus point of the cylinder will be focused automatically onto the second focus point. That is the light in this case that is the light in case emitted from the focus 1 of the cylinder will be focused at the focus 2 of the cylinder, either directly or by reflection from the inner walls of the cylinder. But you know that if we have a non-elliptical cylinder, that is, it is not of the elliptical type, then of course you can place the flash lamp and the active medium very close to each other. And you see that the cross section of this geometry shows that this is a non-cylindrical shape. So in the non-cylindrical shape, it is also required that the inner surface should not be specularly reflecting, because if it is specularly reflecting, it will not be focusing the light from the flash lamp onto the active medium. So it must be diffusely reflecting surface. That is, the inner surface of this non-cylindrical geometry should be non-diffusely reflecting, so that it can equally receive light from all directions onto the active medium. If an intense pumping is required, a cylinder with a cross-sectional area consisting of two ellipses with three foci axes, that is F1, F2, and F3, with the central focal axis acting as the common axis of the two ellipses, is used and is shown in figure number 3. For example, look at this figure. And if you look at the cross section of this figure, it will appear to you that as if we have joined two elliptical cylinders. So here this geometry contains two elliptical cylinders joined together, such that it has three foci labeled with F1, F2, and F3, whereas the F2 focal point is the common focal point for the F1 and for the F3. That is, F2 can be regarded as the common focal point of the dual ellipse cylinder. And you see that this is an encapsulating dual ellipse cylinder. So we can have a specular reflection inside this encapsulating cylinder, so that the light can be focused maximum to the active medium rod. And you see that the flash lamps, which are now located on focus point F1 and F3, will be focusing the light enormously at the active medium rod located and parallel to the flash lamps at the focus number 2. And the caption of the figure is dual elliptical cylinder containing active medium rod along the common foci and the flash lamps along the other two focal axes. So you see that this is why we use, because we want to have active medium rod to be pumped enormously. That is a strong pumping is required in this case. The two lamp sources are placed at F1 and F3, whereas the active medium rod is placed along the F2 axis. The inner surface of the encapsulating cylinder is specular. So you see that when we are using the encapsulating or elliptical cylinders, for the elliptical cylinder geometry, we want to have specular reflections coated inside the inside wall of the elliptical cylinders, so that after reflection from those one, the light could after the first reflection, the light could reach the active medium from these flash lamps. The energies from the two lamps are focused on the laser rod after single reflection from the inner surface of the encapsulating cylinder. In the close coupling configuration, you see that this is the cylindrical elliptical cylinder configuration. But you see that if you don't want this ellipse cylindrical formation and you want to use an ordinary formation geometry, then you need then you can place the active rod very close to these flash lamps, or the two flash lamps can be placed very close to the active medium rod. In the close coupling configuration, the flash lamps and the active medium rod are placed in a cylinder with diffusely reflecting inner walls as shown in figure number 4. So you see that in this geometry, which is a cylindrical geometry, you can say, for example, but this is not an elliptical cylindrical geometry. It could be of any shape. For example, you can look at this at the cross section, this one, that it is not of elliptical type. Though it is an encapsulating cylindrical form, but it is not of elliptical type. So it means that the inner coating at this surface should be diffusely reflecting. So the inner surfaces are coated with diffusely reflection coating, and you see that you can have, again as in the previous case, two flash lamps lying very close to the active medium rod. And the flash lamps are parallel to the active medium rod, so that they can impart maximum energy to the active medium rod. And the light which will not reach directly from these flash lamps onto the active medium, they will reach the active medium rod after diffuse reflection, because we have diffusely coating, we have diffuse reflection coating inside this cylinder, so that the light after reflection can reach the active medium rod uniformly from all directions. So this is the caption is non-elliptical cylinder containing active medium rod and two flash lamps in a closed assembly. For higher powers or energies, multiple flash lamps with multiple reflections are used to pump an active medium in the form of a single slab or multiple slabs. You see that here we can use the active medium in the form of a slab. And then we can use multiple slabs as the active medium, and similarly we can use multiple reflectors. And multiple flash lamps with multiple reflectors can be used when we are using the active medium in the form of a single slab or multiple slabs. Laser beam follows a zigzag path in the slab, and the two end faces of the slab act as reflectors. Such a configuration is preferred when the laser beam of very high optical quality is required, because the birefringence stress effects and the thermal effects are averaged out in such a cavity. You can have a look at this diagram. The caption is an array of flash lamps and reflectors for uniform illumination of slab as the active medium. So you can see that there is a slab over here through which the light is passing zigzagly. So here the beam will enter, and then of course it will undergo multiple reflections within the slab, and then it will leave at the other end as an output beam. So here this portion of the slab is acting as an output coupler from which the light can be obtained, whereas a total reflecting surface can be assumed on this side. So this side of the slab is totally reflecting, and this side of the slab can be regarded as partially reflecting and partially transmitting. And the light will go making a zigzag path between these two end faces. And you can see that you can see parabolic shapes over here containing these circles are actually the end faces of the flash lamps. The flash lamps are running parallel to the axis of these parabolic cylinders, parabolic paths. So you see that you can see these circular are actually the flash lamps, and the other ones are the parabolic refractors. So on the top we have the parabolic refractors, and at the bottom we have the parabolic reflectors. And at the foci of these parabolic reflectors we have the flash lamps, so that the light could be incident on the slab uniformly from the top and also from the bottom. And you see that this is the slab, and the slab is acting as the active medium. Each reflector is a parabolic reflector, with each flash lamp located at the parabolic axis to generate a uniform beam for uniform illumination of the slab active medium. The slab end faces are cut at the Brewster angle. Each reflector is a parabolic reflector, with each flash lamp located at the parabolic axis to generate a uniform beam for uniform illumination of the slab active medium. The slab end faces are cut at the Brewster angle. So this end and this end are cut at the Brewster angle, so that the light becomes polarized and the quality of the light beam can be improved. The transverse dimensions of the beam depend on the transverse dimensions of the slab. So this is the transverse dimension of the slab, and you need that the spot size of the laser beam will also have a dimension comparable with the dimensions of this transverse dimensions of this slab. The geometry is shown in figure number 5, which I have explained. A few words about flash lamps are now given. Xenon and krypton flash lamps are normally used. A pulse voltage is applied directly between the lamp's main electrodes, which ionizes the gas contained within the lamp, and an intense flash of light is produced. The time constant of the circuit generating the voltage pulse and the electrical characteristics of the lamp determine the duration of the flash. It varies from millisecond to microsecond depending on the design. For continuous wave lasers, a current regulated power supply is used. A triggering pulse from these sources must be very high in voltage and be much longer in duration. An RLC based triggering electrical circuit is shown in figure 6. So let me explain that figure first. This is figure number 6, and the caption is an RLC based triggering circuit for a typical flash lamp. You can see that this is the power supply. It is actually a DC power supply. This is a resistance. This is a bank. C stands for bank of capacitors. L stands for inductors. This is a flash lamp, and this is the triggering pulse. So triggering pulse is given so that the capacitors, that is the bank of capacitors, could be discharged through the lamp, through the flash lamp when the triggering pulse is received at this coil. So R is actually the resistance and capital L is the inductance. So cap R and C will determine the RC constant for the charging of this bank of capacitors. And capital L is the inductor which limits the current through which limits the discharge current. And the frequency of this lamp to discharge is controlled by the triggering pulse. So C represents a capacitor bank in which energy is stored by charging process with a power supply. Inductor L is used to limit the current of the discharged pulse. The LC network suppresses the ripple if R is replaced with a suitable inductor. So you see that the ripple of the pulse can also be controlled. The discharge current can be controlled through the control of the inductor. And then of course the charging and the discharge, the charging time of the RLC circuit can also be controlled using the components. Xenon flash lamps are used for pulsed excitation, whereas krypton lamps are used for continuous wave operation. At high gas pressures, the emission spectral lines become much broadened. The spectrum from these lamps becomes even more continuous at much higher current densities. So you see that we can broaden the spectrum of the light emitted from the flash lamps either by controlling the pressure, that is at high pressure we can have a more broadened spectrum from the flash lamps, and also by passing a high current densities through the flash lamps, we can produce continuous spectrum, and we can produce even more broadened spectrum and even more continuous spectrum. Now something about the internal process of a flash lamps. The main reason is the electron-ion recombination, which gives off recombination radiation, and the electron deflection when it approaches an ion, giving off Bremsstrahlung radiation. That is the main reason is the electron-ion interaction. So you see that due to electron-ion interaction within the lamp, within the gases, within the lamp, which is within the gas, within the lamp, we can have a recombination radiation, or we can also have a Bremsstrahlung radiation. The intensity I of the emitted light is proportional to the product of Ne and Ni, where Ne and Ni are the densities of electrons and ions respectively. If the gas discharge is neutral, that is Ne is equal to Ni is equal to capital N, for example, then capital N can be written as the current density divided by the charge of electron and the drift velocity of the electron, where V drift is the electron drift velocity. This implies that I is proportional to Ne, as said earlier. And this will equivalently imply that I is proportional to the current density J through the flash lamp. So if you increase the current density through the flash lamps, you can also produce more intense flash light from the flash lamps. For pulsed lamp, the continuous spectrum dominates the line spectrum at higher current densities. In ND-YAG and Alexandrite lasers, ND ion, that is ND plus 3, in the Y3Al5O12 crystal, and chromium ion Cr plus 3 in BeAl2O4 crystals are the trivalent impurity ions which absorb light from lamps and act as active components of their respective crystals. That is, ND ion will act as an active crystal in Y3, an active component in Y3Al5O12 crystals, and chromium ion will act as an active component in the BeAl2O4 crystals. Both Impurity ions have a much broader absorption spectra in comparison with the emission spectra of the xenon and krypton based lamps. Some absorption lines match very well with the emission lines. Even a change of host materials does not affect the absorption spectrum of these ions, as the transition arises from the electron transitions between inner shells of the ions. So you see that here these transitions are relevant with the inner ions, with the inner shells of the ions, that is these ions, that is Nd plus 3 ions and the chromium plus 3 ions. So this technique will work irrespective of the crystal or irrespective of the host crystals. So because the absorption spectrum of these ions is important, and you know that the transitions arise from the electron transitions between the inner shells of the ions. So outer shells are not involved in this case. So the host materials could be anything, and this technique will work. In metal dopant ions such as chromium plus 3, the spectrum arises mainly due to the transitions involving outermost electrons. You see that here we have the same chromium ion over here, but you see that here the transitions will involve, that is the spectrum arises mainly due to the transitions involving outermost electrons. Whereas in the previous case, it was that is only the inner shells of the electrons were involved. And the spectrum is affected by the change of host materials. Since here in this case, for example, in case of a metal dopant ions, the outermost electrons are involved in the transitions, and in the generation of the spectrum, it means that the host material will also affect that thing. So chromium plus 3 in ruby, which has a formula of, that is the chromium is added there, and the formula is Al2O3, and in C and in the LiSF, that is chromium is there, for example, and the formula is lithium, strontium, aluminium, and F6 crystal. And in the LiCaf, the chromium is there, and then the formula is lithium, calcium, aluminium, F6 crystal. So these are the laser materials. For example, LiSF, LiCaf, these are, and the ruby, of course, these are the three very important laser materials. And this is the active component. So in these one, what is the active component? Chromium ion is the active component in these crystals. And the active component in these crystals is important in these important laser materials. So you see that these three, that is the ruby, LiSF, and LiCaf, are the important laser materials. And you see that I have described briefly the functionality of the flash lamp, both externally and electronic point of view, with the point of view of pressure and temperature, and also with respect to the density of these, and also the density of the current. For example, what will be the effect of the density of current on the intensity that that is obtained from the flash lamps, and also the other that's how we can obtain continuous flash lamps and the flash lamps in the pulsed mode. These have been explained in this description, in this lecture. So this is the end of slide number 96.